In this video, we're going to return to function analysis and talk about functions that have domain restrictions or derivatives that have domain restrictions. Alright, here's the first example. So this is a rational function, so we have domain issues. Whenever the denominator, the bottom of this fraction, is 0, then you got to throw that x out of the domain. So let's ask Sage to find out where the denominator is 0. So here's the denominator. I'm going to solve where that's equal to 0. There are 3 places. So the domain of this function is all real numbers except for these 3 things. Here's the set notation way to write that. So all real numbers except -4, -3, and 2. Now those could be either a whole or a vertical asymptote. And we're going to find out which is which by taking limits. So we're going to take the limit for the original function f, okay, not just the denominator now, the original f, the whole rational function, which remember when you type rational functions you need parentheses around the top of the fraction, parentheses around the bottom of the fraction. So we're going to take the limit of that rational function as x approaches each of these 3 gaps in the domain. The first two, at -4 and -3, the limit is infinity, so that means we have a vertical asymptote. And the third one, x equals 2, the limit is -1/30. That means we have a hole. The hole is at the point 2 comma -1/30. Alright, now we're ready to find the derivative. Here's the derivative. If you look at the formula for the derivative, it has the same denominator involved as the original function. This same part, or the same thing squared. It has the same roots for the denominator anyway, so there's no additional gaps in the domain for the derivative. It has the same gaps as the original function has. So we need to find where the derivative is 0, so I asked Sage to tell me where the derivative is 0. There are 2 places. Here I converted them to decimal, so roughly -3.5 and roughly 9.5 is our critical points. I want to see if the sign of f prime actually changes at those critical points and see if we have a local max or a local min. So first off, I took something to the left and something to the right of this one, and there was a sign change from negative to positive. That means the original f changes from decreasing to increasing, so that's a local minimum. I chose something to the left and something to the right of 9.48, and there was a sign change, positive to negative, so that's increasing changes to decreasing. So that gives me a local max at 9.5. Alright, find the second derivative. Here it is. Again, we look at this denominator and we see the same type of stuff involved. It's going to have the same factors in this denominator. So the same places where that denominator is 0, same domain for f double prime as for f prime and f itself. So let's find out where it's 0, and I get these 3 answers here. Notice that some of these have an I. This capital I is the square root of -1, the imaginary number. So those are potentially complex numbers. Now not always. Sometimes when an I shows up, it's sort of a mistake. Like if you would just simplify it, the I would cancel out and it would actually be a real number. We'll see one of those later, I think. But in this case, the first 2 are actually complex numbers. You can see that here. Here's an imaginary part of this number. So we're not going to care about those. We're only dealing with real numbers. Those imaginary ones won't show up on the graph. Now I just manually copied and pasted. Okay, notice this says x equals blah 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 blah, and then comma is where that one ends. So I copied this down here and I put capital N around it, and then I went to the next line and I copied this one, and finally I went to this one and copied this one. And it's only the third one that is actually a real number, about 16. That is my potential inflection point. To see if it's an actual inflection point, I'm going to choose something to the left and something to the right. Did the sign change? Yes. Negative to positive. That means that there is an inflection point around x equals 16. X and y intercepts. So here, solve where the function itself is 0. That's the x-intercept at 3. 0 is in the domain, so I calculate f of 0. It's -1/4. That's the y-intercept. Determine the end behavior. So I take the limit at -infinity and the limit at positive infinity, and in both cases I get 0. That means the line y equals 0, which is the x-axis, is the horizontal asymptote for this function. Okay, ready to make an informed graph, I need to make sure I cover all my critical points and x and y intercepts. So I'm going to take the critical points from up above, I'm going to plug them into the function. The reason I'm doing this is to see what y values go with them, to give me an idea of what my y min and y max should be. My x min and x max needs to make sure they cover all of these points. So here's my first attempt. I put x min at -5, so this was sort of the smallest of my critical points, so I went down a little bit. This was the biggest critical point, about 16, so I went up a little bit to 20. In the y direction, the biggest y had come out was this 26 roughly, and so I went up to 30. The smallest, I think, was actually the y-intercept up here at -1/4. Just for the sake of balance, since the maximum was 30, I put the minimum at -10, just so they'd be kind of like, I don't know, I didn't want to put the negative, like -1 to 30 didn't seem quite right to me. So here's kind of my first attempt at the graph, and not perfect. Oh, actually I forgot to mention here, this is the smallest critical point, but then we also had the domain issue. Remember, there was the gap as a vertical asymptote at -4, so I needed to make sure I included that one too. I almost forgot about that. There's another good reason why you should write these things down on a piece of paper so you don't have to scroll back and forth, and it might save you some trouble missing something. Okay, now this is not a great picture. One, we hardly see this branch of the function over here. Now we know there is no x-intercept, so it never crosses the axis. We know there's no local min or max, so it doesn't turn around. There's no inflection point, so this is just decreasing concave down forever, and this is the horizontal asymptote, the x-axis. So this just approaches the x-axis and flattens out, and this is a vertical asymptote. This just goes down, shoots down towards that, that vertical line. So we can see the shape of it, though it's not clear. I mean, we know this pattern just continues, but I'd really like to go a little further than that, so I see more of that. I can't see much of this thing up here, so who knows, maybe you want to go a little higher and see more of that, I don't know. Bigger problem is this branch here. It looks like it's just increasing concave down forever, and we know this x-axis is a horizontal asymptote, so maybe you would think, okay, this is increasing concave down, it just approaches the x-axis from below. Now you can kind of see some blue here, and not hard to tell where exactly that is. Actually, this thing crosses the x-axis. In fact, we know that because we found these x-intercept. Remember where the x-intercept was? At x equals 3, it crosses the x-axis. And there's also, we see one local min, that's the -3.5. There's a local max. The local max was at this guy, like 9.5. So it crosses the axis at 3, it goes up, and it peaks around here, and then it heads back down again. There's also an inflection point here at 16, and so it's concave down, and then it actually bends to concave up, and then approaches the x-axis from above. So it's not clear what's happening here from this graph. Now, in order to see that sort of crossing and then turning and then bending, all that stuff, it's going to be very difficult to see that, and also see this branch up here, this little almost like parabola looking thing at the top. Because these are so far apart, if I zoom in on this rightmost branch in order to see all those key features that I calculated from my calculus, I'm not going to be able to see this thing unless I have a massive graph that takes up the whole room. So probably there's no way to have one picture that shows everything. I'm probably going to have two pictures. One kind of like this overall shape that shows the 3 branches, and then a second one that kind of zooms in to show the key features here. Okay, here's the second graph. So I went out further in this way so I could see the horizontal asymptote better, see more of that one. Kind of scrunch this part down. I marked the local min. I marked the local, sorry, that's the x-intercept, the local max, and the inflection point. So now that they're marked, I can see that, okay, I know something's there, but it's not obvious what. The other thing I marked is the hole with this open circle. Let's see, where does that happen? Right here, this point. And I'm not going to ask you in your assignment to mark any holes. I'm not sure you even have a hole on your assignment. But if you want to do an open circle, that is a way to draw an open circle. With the point command, this faceted equals true is what makes it so that it has, the outside and the inside are different colors. The color white is the inside color, and the marker edge color blue, that's the border around the outside. That's how you make an open, or well, a way to make an open circle. So this is fine. Oh, I replaced the vertical asymptotes. Remember up here, Sage has drawn in these things. These are not actually vertical lines that it's drawing in. Those are actually a mistake. The way that it's plotting, the computer just connects dots that it calculates, and so it thinks those are actually part of the graph. We know they're not. You can turn those off with this command, not command, but this option within the plot. So this is the plot of the original f, and I have this detect poles equals true. That detects that vertical asymptotes, and so it doesn't graph those vertical line segments. Oftentimes those asymptotes are marked with dotted lines, or dashed lines, I guess. I just added in lines. A vertical line is not a function, so you can't use the plot command for that. So I just used a line and made the line style dashed, and I'm not going to ask you to do that either. You can just leave these here, and as long as you recognize those are the vertical asymptotes and not actually part of the graph. Okay, now I need to make a second picture to see these key features here. So I just zoomed in really close on this, and I knew what kind of values I want here because I calculated. Remember, I calculated up here at the beginning. These are the values for my the y values for the local max and for the inflection point, and you can see they're about 0.04, so that's why I have 0.04 here. And just for balance, I kind of was symmetric there. So here's my hole, here's my x-intercept, here's my max, here's my inflection point. Now I can see what's happening on this right side. It's a really small wiggle here on the hundredths. Okay, and now if you look back at these graphs, you can do increasing, decreasing, concave up, concave down. Don't forget the hole at x equals 2. Oftentimes when I talk through this, I leave out the 2. So I want to try to remember, break up these things. We can't mold these two together because there's 2 is not in the domain of this function. There's a hole there. Same thing up here. I really need to leave out 2. So from this graph, I can see decreasing negative infinity up to the asymptote at -4, decreasing from -4 until you reach this local min, which is -3.48 and change. From there until -3, this other vertical asymptote, it is increasing. From -3 until you reach the hole, it's increasing, and actually I should go down here now. -3 until 2. From 2 to 9.5, roughly, it's increasing. From 9.5 off to infinity, it's decreasing. Concave down, negative infinity to -4. Concave up from -4 to -3. Concave down from -3 until the hole at 2. From 2 until roughly 16, concave down. From 16 to infinity, concave up. Okay, that's what we see here. Alright, this example will have a different kind of domain restriction. We have the natural log function involved. And remember, natural log, if you're dealing with real numbers anyway, is only defined when x is greater than 0. And the other issue here is division by 0, so that means x is not 0. And that's already included here in the natural log part, so that's nothing new. The domain of this is 0 to infinity. There is no other vertical asymptotes or holes within the domain. There's just this boundary of the domain at 0. What happens there, is it a hole or is it a vertical asymptote? You take the limit. As x approaches 0, we get minus infinity. That means it's a vertical asymptote. So vertical asymptote at x equals 0. Here's the derivative. If you look at the derivative, remember log in Sage is natural log, so that's what we normally say ln. The domain of this derivative is the same thing as the domain of the function, so nothing new there. There is one critical point where the derivative is 0 at x equals e. Remember, e is not a variable, e is a number, it's roughly 2.7. Let's see if the sign of f changes, so I went something to the right. to the left of e and to the right of e, the sign changed, positive to negative, that's increasing to decreasing, gives me a local max at x equals e. Here's the second derivative, again, same domain as the first two, f and f prime. One critical point for the second derivative, where the second derivative is 0, that's at e to the 3/2. Here I calculated it, it's roughly 4.5. That is my potential inflection point. Is it an actual inflection point? I took something to the left, I took something to the right, did the sign change? Yes, so there is an inflection point, roughly 4.5. X and y intercepts, so there is one x-intercept, so I set the function equal to 0 and solve for x. X equals 1 is my x-intercept. 0 is not in the domain of this function, so there is no y-intercept. End behavior. Now this end behavior is slightly different from the other examples we've done because this function doesn't have anything in the negative side. You wouldn't take a limit at negative infinity because there is no x's over there as far as this function is concerned. The domain of this function stops at 0, and so we can approach 0 from the right, and that will give us the end behavior there. That tells us negative infinity. Now we've already done that because I did it earlier, it's a vertical asymptote. I'm doing it again just for emphasis sake. So there's a vertical asymptote at 0, that's the left side of the domain. The right side of the domain is infinity, and that gives us 0, so we have a horizontal asymptote at y equals 0. So the y-axis is a vertical asymptote, and the x-axis is a horizontal asymptote. Okay, I need the values of the function at these key points. So this was my x-intercept and my local max, and then the inflection point. So I plugged in the x value for the local max into the function, and the x value for the inflection point into the function. That gives me an idea of how big the y value should be. This is, maybe a half. So that's what I did. Y max is a half, and just kind of to balance it out, I put y min at negative a half. X min I put at 0 because that's where the domain starts. I stopped x max at 5. My biggest value from up here in my analysis was this guy, which was roughly 4.5. Okay, so this is my first attempt. It's not a great graph. I mean, it's okay. It shows me this is concave down here and increasing until the peak and then decreasing. What I can't see is an inflection point. There's an inflection point right around there. And inflection points are hard to see if you don't have enough graph on either side to show the bending. This changes from concave down to concave up. So it's actually concave up right here in this little segment, which is very difficult to see on this graph. I'm going to need to make my x max a lot bigger. Now the vertical asymptote at 0 is not really obvious here either. I mean, the vertical asymptote could be at a half for all we know on this picture. So here's a second attempt. I went out further. Now there's nothing, there's no important features out here, but I want to go out that far just so I could see this bend. So I set x max at 25. Vertical asymptote's starting to become a little clearer over here. Here's my x-intercept, my local max, and my inflection point that I've marked. This is a complete enough picture. Now it's not immediately obvious that the x-axis is the horizontal asymptote. It could be at a tenth for all we know here. But we calculated it. We know this is actually approaching the x-axis. Now, if you wanted to see that clearly, you'd have to go out quite a bit more. So, step 11. There is, I just realized I forgot to mention something about the max and min in the last problem, the last example. Well, there was none. Anyway, this one does have an absolute maximum. This local max is actually an absolute max. The function never gets higher than that. The absolute max is roughly this, well, here's the value I calculated. It's f of e. The exact value is actually 1 divided by e, which is roughly 0.37. There is no absolute min because this thing just keeps going down in this vertical asymptote. It's increasing from 0 until the peak at e. It's decreasing from e on up to infinity. It's concave down from 0 until the inflection point at e to the 3/2. And from e to the 3/2 on, it's concave up. One last example. And this example, we have a domain issue with the derivative. So here's my function. The domain issue with this guy is division by 0, potentially. But that never happens because x squared plus 1 is always positive. Okay, x squared is greater than or equal to 0. You add 1, you're greater than or equal to 1. I don't need to worry about the roots. These are odd roots. So odd roots of negative numbers are fine. So I don't need to worry about the roots. So the domain of this thing is actually all real numbers. Now here's the derivative. And the derivative now has a domain issue. Because this guy, x squared plus 1, that still can't be 0. But this guy right here, x squared minus 6x plus 9, that's a different story. So first off, let's figure out where the derivative is undefined. And like I said, the issue is when this part is 0. The rest of it is not going to give you division by 0. So I asked Sage, when is that equal to 0? And there's one place, x equals 3. This is actually x minus 3 all squared. So derivative is undefined at x equals 3. That's a critical point. This is the first time we had a critical point where the derivative was undefined. We also need to find out where the derivative is 0. So I asked Sage, where is the derivative 0? It gave me 3 answers. This is a little bit disturbing because it actually gives me x equals 3 here, and I just determined that f prime of 3 doesn't exist. This is actually a mistake that Sage has made. It appears that as part of the solving, this is not a vertical asymptote. This is actually a let's see, is it a whole? I forget now. But anyway, some of this would cancel, and anyway, that's what happens. So be on the lookout. I guess if you forgot to check for this, it'd come out again anyway. I mean, it's a critical point whether it's undefined or 0. But the function here is defined at 3. So you might have a local max or min at 3. The problem is this is not a rounded mountain or valley. It's a sharp corner, as we'll see on the graph. Okay, so let's convert these two to decimals. These are the other two values where the derivative is 0. And so I have these 3 critical points. I'm going to see if the sign actually changes of f prime. So went ahead and plugged those in, and the sign did change from negative to positive. There's a local min at x equals 3. We'll take this next one, the negative 3.85, something to the left, something to the right, plug it in. Did the sign change? Yes. Negative to positive, another local min at negative 3.85. And then the third one, negative 0.65. Something to the left, something to the right. Did the sign change? Yes. From positive to negative. That means we have a local max there at roughly negative 0.65. All right, here's the second derivative. We have the same domain issue going on. So f double prime of 3 does not exist. I asked Sage where f double prime is equal to 0, and I get a huge mess. Notice the mistake again, x equals 3. Ugh. And there are 4 other solutions. Okay, take my word for it. Here's one. This is the first one, I think. There's one. Notice the comma. Here's the second one. Now, there is a way to, let's see, where does it go? It stops there. There is a way to kind of pick out these solutions individually. I'm not going to worry about that. I'm just going to carefully copy and paste. So here I did. I copied and pasted all those big ugly messes in there. And here's what comes out. Now, all 4 of these have this I, the square root of negative 1, in the answer. And so we might think, okay, this is a complex number. We can ignore all of these. However, this is actually a rounding error. If you look at this decimal approximation here, notice this scientific notation. This is not 5i. This is 5 times 10 to the minus 17, which is very close to 0. There's a very good chance that that's just a round-off error in this numerical approximation. If we looked at the original exact answers up here and we simplified those algebraically, it would be a nightmare. But if we did it, we'd see that the imaginary parts actually all cancel out. And these are real solutions. So this is kind of a computational error involved, a disadvantage of doing things on the computer. We'll also be able to tell that in step 7 to check when we check and see if the sign actually changes. We'll see that these are in fact inflection points. So it'll confirm my suspicion that this is just rounding error. And so we have 5 critical points, the x equals 3 where the second derivative doesn't exist, and then these 4 where the second derivative is 0. And if we plug in numbers to the left and right of 3, the sign does not change. So that's not an inflection point. When we plug in numbers to the left and right of the second one, the sign does change, negative to positive. So there's an inflection point there. The sign changes to the next one, so there's an inflection point at the next one. And here is the third one. The sign changes there as well. Here's the fourth one, 2.15. Something to the left, something to the right. The sign changes there as well. So we have 4 inflection points, and then x equals 3 did not have an inflection point. We'll see on the graph what happens there. There is one x-intercept, which is x equals 3 again. So that's, remember, it's in the domain of the original function, and that's actually x-intercept for this function. There's a y-intercept. It's the cube root of 9, which is roughly 2.1. In behavior, as x goes to infinity or negative infinity, in both cases we get infinity, so no horizontal asymptotes for this thing. Alright, make an informed graph. So here is the important x values that came out of our analysis above. I did f of 3 again. That was my x-intercept, so that's kind of redundant, but that's okay. Plugged in all my critical points to the function, and these are the numbers I get. So it looks like between 0 and what's the biggest one? This is the biggest one. So maybe, what did I do? 0 to 3. Okay, that seems reasonable. In terms of my x-axis, the smallest thing up here is this one. The biggest one is this 2. So I went from negative 20 up to 5. A little bit bigger than these numbers that I got. I went ahead and added in the points. So this is an inflection point, which is not immediately obvious, but changes here. This is concave up. You can see that little bend. It's actually concave. Wait, isn't that an inflection point? Concave down there. I'll have to look. Hard to see. The function is concave down on the left side, but if we went far enough in the negative direction, it would obscure the rest of the graph. Okay, well, can't see this concave down very well. Concave up here, concave up until there. There's the next inflection point. Then it's concave down. Here's the y-intercept. This is an inflection point too, if I remember right. So yeah, so concave down changes the concave up right here. Another inflection point changes the concave down here. It's also concave down over there on this side. So this is kind of a complicated one. It's really hard to see those inflection points and the change in concavity. So it's a good thing we have our analysis up above. Go back and look at those. The sign of the second derivative, you can see where it's concave up and concave down. It's hard to see it on this graph. Decreasing this whole way until you hit the local minimum here. Then it's increasing until the local max. Then it's decreasing to this local min, and then it's increasing. There is no absolute maximum here because remember the in behavior, this keeps going up. There is absolute minimum right here. Y equals 0 is the minimum value of this function. Occurs at x equals 3. Okay, and then I went through the increasing, decreasing stuff. Here's with the numbers on it. So I'll let you look through that. Remember the numbers here that on the concave up, concave down, those are the places where the second derivative is 0 or undefined. And increasing, decreasing, those boundaries is where the first derivative is 0 or undefined. Again, if you kind of write those down on a piece of paper, have them handy, you'll be able to tell which numbers you should put here as you look on your graph and find out what's what. Now again, on your assignment, I'm going to go through with you the first problem in class. You can start it at home if you want to, but I will go through the first problem in class. You'll have the rest of class to finish the second problem.